bad. My daughter wrote me a doctor note so I can explain. So it says, "Dear Zoom people, I'm afraid Professor Getz's voice is off. Indeed, you could say it sounds like he just smoked a pack of cigarettes. Thankfully, it's not the case. In fact, he has a minor case of seriousness. The reason it's affecting him so bad is because he's never been serious before, and therefore this illness should be treated with caution. And it's assigned by an anonymous, awesome doctor. But I have a cold, but anyway, so that's my doctor's note from my daughter. She forced me to read it. Okay, so last time we talked about this Poisson summation conjecture. And the basic import is that there's some notion of Schwartz space for some nice affine schemes X, together with some Fourier transform on it that satisfies some equivariance properties, and then Poisson summation holds. And if one can prove this, then lots of fantastic things follow in the Langlands program, but I sort of want to forget this for the moment and just sort of emphasize that this sort of, whenever you can create this setting, you have a whole new playground in which you can try to apply the ideas of harmonic analysis, and in particular the circle method. So we can ask and perhaps answer any question on X that we asked for vector spaces. So for example, and this actually came up in the comments the other day, or yesterday rather, when somebody asked about what's the analog of convolution of in the Fourier transform. Well, I don't know whether there's an analog of that, but one thing that you can ask is you can ask for characterizations of the Fourier transform. You can ask for things like Riemann-Lebesgue. Probably misspelling Riemann here, but Lebesgue, but ask for things like the Riemann-Lebesgue lemma and variants of this. You can ask for developing analogs of stationary phase adapted to the geometry of the situation you're studying. And more generally, you can just ask for any question that you ask in the circle method. You can ask it for a vector space replaced by this space X. And so to give you a feeling for what that sort of thing might look like, I want to talk about there's only a handful of cases where the Poisson summation conjecture is known in any sort of, with any degree of precision. And I mean, you can use them to build other cases, and I'll talk about how you can sort of splice things together. But you know, each of these cases has a very interesting geometry, and like I said, you can, any question that you've thought of in the context of the classical circle method, you can ask the same question on these spaces and see if you can get some sort of answer, right? So I'm going to warn you of a notational abuse. So when I'm working in a local setting, so if I've fixed a place V, then I'm just going to write F for FV, this completion. All right, so this is just some local field. It's sort of easy to see why you make this abusive notation. You don't want to be carrying this V around everywhere. It just clutters the notation. Okay, so here's the first example. The cone. All right, so I give myself some quadratic, so I guess in this case I want to just give myself a split quadratic form. So let me give myself a split quadratic form from, or let's say it's a symmetric bilinear form. that has a maximal isotropic subspace, although it's not so important for this. And we can define an associated quadratic form QU equals 1/2 UU. And then we have, I think I mentioned this last time, the affine scheme that's just the vanishing locus of this thing. So it's the R or Y and R to the N such that Q of Y is equal to 0. So it's just the 0 locus of this quadratic form. And this was the example that we started out our whole discussion with, which was, well, can we understand not this space via Poisson summation in the traditional sense, but can we actually, is there a notion of Poisson summation for this space? And the answer is yes. So there is Poisson summation. There exists a Poisson summation formula for C. But I want to talk about what the Fourier transform is for this. So there's a notion of Schwartz space. I'm going to defer the notion of the Schwartz space for now. It sits inside L2 CF. And there's some Fourier transform on CF. It takes it to itself. So I want to give you an explicit formula for this Fourier transform because I think it's quite pretty to see how these things work. So let's just choose a differential form omega q such that if I take omega q and wedge it with dq, I get the measure on the whole space, the whatever measure gives you the R measure on the vector space. Okay, so here's the formula. So this is recent work of myself, my student Chun-Chen Su, and my postdoc Spencer Leslie. So if I take F in the Schwartz space, and I'm saying Q is split here, then the formula for the Fourier transform is the following. So remember, psi is this additive character that I was working with at the beginning of this lecture series. Okay, and this is the norm on that field. Let me just make sure that this is a psi. And then I have to take this and integrate it times the integral over CF of F W psi of W T to the 1 plus Pn W, oh, I think I want to W prime. W prime times omega q, and the whole thing dt. Okay, and Pn is just a parity thing here. It's congruent to n mod 2. So I choose it to be 0 or 1. Okay, so let's sort of investigate what this thing is. So if you had to guess what the Fourier transform on a cone would look like, well, what would you do? Well, you have a natural pairing on the whole vector space, which is just the pairing that you started with. So you could just say, okay, well, I'll just integrate that pairing over the quadratic form and choose a suitable measure on the quadratic form, make it algebraic because that makes us happy, right? And if you did that, you'd get exactly this expression here, where you're just integrating over CF and then you have this natural pairing. And that's almost right. And the thing that makes it you have to adapt it a little bit. And the adaptation is there's an additional integration over F times with respect to some explicit measure. So, I think this is quite pretty that, it's sort of the naive guess, and then there's a correction that you can write down explicitly. Okay. So, and I'm going to talk today about a family of examples where this sort of phenomenon is valid, that you always have this sort of formula for the Fourier transform.
What is the content of this theorem? It seems like this is a definition.
No,
the
so
left-hand side has an a priori meaning.
So the real content of this theorem is that the Fourier transform was actually defined in a different way originally that I didn't, I haven't given you. So the way that the Fourier transform is defined is it's defined in terms of a normalized intertwining operator on an appropriate Eisenstein series, degenerate Eisenstein series. And so it's not clear from that description that you get something that honestly looks like a Fourier transform. So there's, maybe another way to say it is, you could take this as a definition, which I think is the complaint, right? That, am I just defining something? So, one way to put this is that if you make this definition, then the Poisson summation formula holds if you choose appropriate basic functions. Another way of putting it is that the original definition of the Fourier transform FC, you can take one of two choices. One choice is a lift of a normalized intertwining operator. Okay, and maybe that if you've thought about these things before, then this will, when I talk about these spaces from a different perspective, it'll be easier to see what this is. And there's another perspective which is using the minimal representation of O n plus 2 when n is even. And in fact, using this second, and maybe afterwards, if you're interested in this sort of perspective, I can talk about it. But all I want to mention is that using this perspective, Gurevich and Kazhdan obtained the same formula. Even if the space isn't split, and over Archimedean fields using similar techniques that of Gurevich and Kazhdan, let's see, Kobayashi and Mano obtained essentially the same formula, but so the derivation that we give in this paper actually works in the context of something I'm going to call Braverman-Kazhdan varieties, or Braverman-Kazhdan spaces, and it works completely uniformly. Whereas if you look at the proofs in these two cases, they rely very heavily on this minimal representation, and in particular, their proofs don't generalize even to odd n. So. So let me also mention while I'm here that, you could ask, well, what's the basic function in this case? So the basic function. So this is, remember, this is something that you want to be fixed by Fourier transform. And this is some non-Archimedean gadget. And it turns out that the formula is k equals 0 to infinity of q to the k n minus 2 over 2. I hope I'm getting this right, but it'll be close enough for purposes of what we're doing, where var pi is a uniformizer. And Q is the order of the residue field. So if you're working over Q, then this is just P and P. Okay. All right. So what's interesting about this is that it very much wants to be the integral points of your scheme of this cone, but somehow because the cone is singular, it has this singularity at 0, it has to blow up as you approach 0, and that's what this infinite sum over k is doing. It's saying that if your point that you're evaluating this as is divisible by many powers of p, then this thing gets bigger and bigger. Okay. But in any case, I mean, at least in this case, it's a very concrete function. So let me also remark that only know a full Poisson summation formula if I explain, or if I give the boundary terms as residues of Eisenstein series. And I mean, I don't really want to get into this, but I just want to, other than to say that this is not satisfactory, what you really want is you want a more geometric. All right, and I mean, in the statement of this is talking about harmonic analysis on the cone. I mean, there's no mention of Eisenstein series anywhere. So in the statement of this Poisson summation formula, it shouldn't have Eisenstein series pop up. It should be something geometric, maybe related to cones on smaller dimensional quadratic spaces. All right. So this is just sort of an example of a case where we can say something about these Poisson summation formulae. And even in this case, you could ask questions like, say you wanted to study circle method problems where you wanted to look at a space that's cut out by a quadratic plus some other. So for two cones, I can give, in one case, I can give it, where in sort of a degenerate case. But I mean, in general, for the intersection two cones, I don't know what the group action is on it. However, what I'm asking, and this is a good question that was just posed, is, I mean, why not try to use this to study the intersection of two cones? So you already have one cone built in, and then you try to use Poisson summation and circle method type methods to study the intersection of this cone with another cone. All right. So here's the sort of family of examples that after vector spaces that we kind of understand the best. So let me get into that. Okay. So this is section 3. Braverman, Hausdorff spaces. This is geometry. So I want to give a bunch of examples of spaces where we know Poisson summation formulae and sort of give you a hint of what the geometry looks like, because it's quite pretty. So let me start by saying, when is the Poisson summation conjecture known? Or in what context, maybe, is a better way to say it. So certainly vector spaces we're good with. And this is essentially the only case with complete understanding. All right. The second case, which is sort of second best in our understanding, is Braverman-Hausdorff spaces, which I'll define in a moment. They're also called pre-flag varieties. And so the names attached to this are, of course, Braverman and Hausdorff, myself and Liu, myself and Sue and Leslie. Again, this is my student Chun-Chen Sue and my postdoc Spencer Leslie. who's coming on the job market this year, and he'd be an absolutely astonishing hire, by the way. Gurevich and Kazhdan, Zhang, Luo, and Zheng have a recent paper on this stuff. And I'm sort of the stuff that's more about the general framework and conjectures that's due to Cho, Go, and Yannis Sakalides. I'm not going to mention in this list. Triples of quadratic spaces. Getz, Liu, Getz, Su, Leslie. There's an analog that I mentioned briefly earlier, which is an automorphic twisted count over a quadratic space, or over a cone, and this is due to Pam Gu, who's another of my students. And this, so I mean, this is up on the archive. Okay, and then there's a new example that basically I'm not going to talk about this time, but this is joint work in progress with Youngju Che over here at Postec. All right, so I'm going to focus on the Braverman-Kazhdan space for now, because this is sort of the best developed, and there's lots of neat geometry that we can talk about. So I'm going to start with the general setup. If you like the general setup, great. If you don't, I'm going to give basically all classical examples in a moment. So G here is going to be a simply connected group. P inside G, a parabolic, which is the same thing as saying that G mod P is projective. And P equals Mn, the Levy decomposition. And if you're not familiar with these things, again, I'm going to say exactly what all these things are in all the classical cases in a moment, but it's useful to sort of set up the notation. So I'm going to set XP circ to be P derived mod G. This is a Braverman-Kazhdan space. So it's almost a flag variety in the sense that if I map down, it has a map to G mod P, which is a generalized flag variety. And it's some torus bundle over this. So, and I'm going to let XP be the affine closure of this thing. So what what you can think about this as is there's a so-called Fluker embedding from XP in general into some product, some product of vector spaces, and you take the closure. So take closure. I apologize, my hand keeps on moving this thing. Okay, so now I'm going to work this out for the classical groups. And I'm only going to take P to be maximal. We'll see what, explicitly what you get out of this. Okay. So in this case, okay. And I'm only, of course, going to work up to G conjugacy. All right. So maybe that's bad Blackboard technique. I'll put that down. Okay, so G equals SLN. Then I have parabolics that are indexed by 1 less than or equal to k less than or equal to n minus 1. And my Levy decomposition, the M is just things that are on block diagonals. So this is n minus k cross n minus k. And this is k cross k. So I'm just thinking about everything in SLN that has this form, block diagonal. And then my nk is everything that's got junk up in the top right corner. All right, and then pk, as always, is mk, nk. So nk, I mean, the fancy way of saying is nk is the unipotent radical of this thing, and then mk is sort of complement to it that's reductive, right? So then if you think about what this is, if I look at SLN and I mod out by pk derived, so just to remark, when I take this derived group, this mk thing, I mean, it started out as being matrices that have where the determinant of the upper block is the inverse of the determinant of the lower block because we're in SLN. And when I take the derived group, I just get a copy of SLN minus k and SLK. Okay, so this thing, if I want to think about it in terms of matrices, so it's all I care about is the last k rows. And I can think about SLK acting on these last k rows. All right, so V1, V2, or VK. And then this Plücker embedding that I mentioned earlier is the natural thing. So I have P derived K SLN mapping into wedge K GAN. So it's the kth exterior power of this vector space, and it just sends my V1 VK to V1 wedge VK. All right. So, and if I take the closure of this thing, all I'm doing is this actually, if I think about it, it lands in the complement of 0 here, and the closure just adds 0. And it'll turn out that in each of these cases, this closure XP is just going to be, if I'm working with a maximal parabolic, all that I'm doing is I'm just adding zeros. So the singularities of this thing are just the point 0, right? So if you want to think about this thing geometrically, it's, well, what are you doing? You're taking essentially a k-plane, but then you're remembering a vector in this one-dimensional space of V1 wedge VK inside this other thing. Maybe that's not the right way to say it, but maybe I'll retract that statement. But anyway, you can think about it as these last k rows of the SLK conjugacy, right? And when k equals 1, then you're just getting wedge 1 GAN, which is just GAN. So you just get the vector space. All right, let's look at the case G equals spin. So I said simply connected, so I have to do this nonsense with spin groups. But I am going to be lazy and just cheat. And I'm going to look at ON instead, because it's easier to describe what's going on and it's good enough for our purposes. So in this case, the maximal parabolics are indexed by 1 less than or equal to k less than or equal to n over 2. Okay, so maybe I'll put it here. All right, so in this case, my mk is g star, where g is in glk and h is in on minus 2k. I'm being a bit sloppy. I should take R points or whatever, but, and the star is, I mean, it depends on the form of your orthogonal group. I mean, if you choose it correctly, it could be inverse transpose or something. My nk is just the upper triangular stuff. So it's I k, I n minus k, I k. I just put junk up here, okay. And I have my pk as before, the Plücker embedding as before. But let me remark that in this case, when k equals 1, we get the cone C from before. So that cone that I mentioned earlier is a special case of this Braverman-Kazhdan space. And in fact, in this cone setting, this isn't true for all the representations, but in this cone setting, if I take spin mod P1, where I take some lift of my parabolic to spin, that turns out it's isomorphic to SON mod P1. So really, I mean, even though I cheated and didn't work with the spin group here, I don't, for the purposes of the cone, it's not really that big of a deal. Okay, and then one more example, and in some sense, if I want to ignore exceptional groups, this is the only other example, and that's when G is equal to SP2N. So, I mean, let me write this down this way. If I let Jn be the anti-diagonal matrix in GLN, then SP2N of R is set of all G and GL2N of R, such that G and G transpose is equal to Jn negative Jn. So I mean, it doesn't really matter what symplectic group I take, but let's just take this. Then again, the maximal parabolics are indexed by 1 less than or equal to k less than or equal to n. And my mk is G H G star, or G is in GL K and H is in SP2N minus 2K. All right, we again have this Plücker embedding from PK derived SP2N to wedge K GA N. All right, and so this has a really nice interpretation. So if I don't do the derived group and I just look at the, if I quotient out and just look at the whole parabolic, then this is the space of isotropic K-planes. And of course, I mean, you know, I mean, if you not, of course, if you haven't heard it before, but I mean, what do I mean by isotropic? I mean that the symplectic form is identically 0 when I restrict to the plane. So all the point of these things is that all of these spaces have rich geometry and they have elementary descriptions. And the point is, for each of these spaces, there's a Poisson summation formula. So if you have some sort of question that you want to ask, where the space that you're working with is cut out of one of these spaces, then you can apply this. All right, and in each of these cases, there's an explicit Fourier transform. I'm going to try to say something about in this lecture. So to sort of move towards saying something about that Fourier transform, let me recall for you each P, we have an opposite. and P op. And of course you can, I mean, this isn't the technical definition of it, but I mean, the idea is really kind of stupid. I mean, your parabolic looks something like this, right? Where you have a bunch of upper triangular things. The opposite is just, well, I just put them down here instead. Okay, so I just flip. So for example, if I take the opposite of the upper triangular matrices, it's the lower triangular matrices. And there's a well-defined way of doing this for any parabolic. And it turns out that if I take this, so in each of these cases, I gave you what the representation, the Plücker embedding embeds into is. So it's this wedge K. So for example, if I take the opposite of this PK parabolic, it's going to embed into the wedge N minus K. And there's a natural pairing that's in, if I have a tensor that's in wedge K and a tensor that's in wedge N minus K, I can wedge them together and I get a pairing. So this persists in general, and right, I get the following. So there's a pairing. As follows. All right, so if I have XP and XP op, then I can embed them into these two representations that I gave explicitly above, VP and VP op. And since these two are dual to each other, I can pair, and then I get some map to GA. So in other words, I have a pairing, right? So finally, I want to say that there's another structure on this that's quite important. So if I let M abelianized be M mod its derived group, all right, and this is the Levy subgroup that I looked up above. And so for example, if I take a look at this symplectic case, this is my M. So my G is in GLK and my H is in SP2N whatever. And if I take this mod its derived group, all I'm left with is just a one-dimensional torus. I'm just left with an F times, a GL1. Okay. So for any of these maximal parabolics that will persist, and this is just going to be GM, multiplicative group. And I have actions M abelianized cross XP cross G to XP, where the abelianization acts on the left and the G acts on the right. Right. So let me say I have a character M abelianized isomorphic to GM, right? And I'm going to normalize everything. So if I take Plücker of M inverse G P, it's omega P of M Plücker G. Okay. All right. So now what I'm going to do is I'm going to pass to analysis in this setting. So section 4, Braverman-Kosztoń spaces analysis. So I essentially wrote down every classical Braverman-Kosztoń space above, right? So let's start by defining, at least in rough terms, what this SXP of F is, right? So first, we have a map it's called an intertwining map, and it takes us from compactly supported smooth functions on G mod this derived group to smooth functions on the opposite. And it's just given by taking F and mapping it to X goes to the integral over N P op of f of fnx dn. Okay. So S of xp f is defined by controlling the behavior of Mellin transforms of f and r p p op f. Okay, so let me say this more precisely. Okay, so if I take a character from f times to c times, so if you want to, you can just take chi to be, I mean, I'm allowing quasi characters here, so I mean, you could just take it to be norm to the s if you wanted. Then you get a map from compactly supported smooth functions on the Schwartz space, the open set, to I chi, and you know, you don't, I mean, this is some induced representation, but you don't need to know what that is for this discussion. It sends f to f chi, which is defined to be integral over m abelianized of f of delta p 1/2 m chi of omega p of m f of m inverse dm. All right, and there's a similar map from xp op of f to what we'll call I bar chi. And let me not, I mean, it matters what this is, but I mean, maybe I'll just suppress it. Okay, I mean here, let me just suppress it. So these things are just Mellin transforms along this m abelianized action. Remember, m abelianized is just isomorphic to f times. Right? So let's assume that f is non-Archimedean. And then let's define S of xp f to be equal to the set of all things f in here, such that f is GO finite. If you don't know what, I mean, maybe it's better to say fixed under a compact open subgroup of G of f, and f chi s is absolutely convergent for real part of s sufficiently large, and G maps to R mod P op f chi s of G divided by some fixed polynomial is a polynomial in q to the negative s and q to the s. And the same thing is true of just the original thing. So if I take G, it goes to f chi s over G. A P P. Maybe I should write, this is just for each fixed B. So this is known as C q to the negative s q. Okay. Where here A, P, and P inverse and A, P, P op inverse are just equal to some product of things that look like 1 minus chi s of var pi to some power times q to some power, etc. So they're just, I mean, these are essentially local L factors. So what you're doing here is you're saying that you're requiring that these Mellin transforms have poles that are controlled by these specific polynomials, right? So the moral is that Mellin transforms are Laurent series in Q to the negative S with controlled poles. And just to mention, in work in progress, we're working on giving something that's more of a function analytic way of thinking about these conditions where you don't have to invoke the Mellin transform. But I mean, it's still, I mean, the thing to think about is that if you say you wanted to understand the usual short space on F in terms of Mellin transforms, I mean, essentially what you'd want is you'd want that when you take the thing's Mellin transform, if you divide it by some local L factor, then you get something holomorphic. So, okay. So in the case of F is equal to C or R, you can proceed similarly. But you have to, there's some more care that's needed. So you have to, if you want to, I mean, in that case, you really want to put a Frechette space structure on these things. And in order to do that, what you'd like to say is, okay, I take my function, take its Mellin transform, and then say that after you divide by some product of gamma functions, then you get a good function. But that really is sort of clunky analytically, and it's better to just fix a vertical strip and say that you take your function and you divide it by some partial gamma factor in that bitter, i.e. a polynomial in that vertical strip. But I don't really want to get into that because it's not very, I mean, this is already the idea. Okay, so then what do Braverman and Kazhdan do? Braverman and Kazhdan define isometries F, P, P op from L2 XP, F to L2 XP op of F. And the isometries are given in terms of a intertwining operator plus some normalizations. But if you want to actually work with the functions, there's some things that are left to be desired by, I mean, what they do is they find a beautiful way of getting things to work with the bare minimum you need to get an L2 theory off the ground. But for example, when they define their Fourier transform, they say that it is defined on a subspace of compactly supported smooth functions that's dense in L2. And you know, you really can't work with something that's that inexplicit. So let's see. So what Spencer pointed out was that there's sort of a nice way to think about what's going on with these Fourier transforms, and using that, this is so this is part of a fairly long paper that just went up on the archive. This is sort of the first half of it. And what we prove is that this descends to the Schwartz space and gives you an isomorphism from one Schwartz space to the other. And moreover, we prove that it has the formula that is similar to what, so it's mu p aug for augmented of f p p geo of f. And I'll say a little bit later what this augmentation is, but the geometric part of the Fourier transform is sort of, if you had to guess, then, and you thought about this a little bit, then this is what you'd get. It's just given by integrating the pairing. So I should put like a variable in here. Right. So it's just, I mean, in fact, this recovers the case of the cone that I talked about earlier. But I just like to emphasize that how natural a formula this is. So what do you do in the case of the standard Fourier transform? Well, you have an additive character on your vectors on F, and then you have a pairing on your vector space, and you just take your function, you integrate against the pairing, right? That's what we expect out of Fourier transforms. And what this formula says is that if you ignore this augmentation operator, which is given very explicitly, and it's the analog in this situation of that additional integration over F times that we saw earlier in the case of the cone, then the Fourier transform is given by the same thing. You take the function and you integrate it over the Braverman-Kazhdan space against this pairing. So I think this is quite pretty that it works out so simply. And just unfortunately, in general, things don't work out this nicely. But I mean, at least in this case, it works out. Okay. So I think what I'll end with today is I'll give some indication of what these augmented operators are. And then next time I'll talk about how you prove Poisson summation in this case and sort of some fun ideas that come up in it. And then if there's time, I'll get on to the other example of these triples of quadratic spaces. Okay, so how do you define these mu p aug? Well, it's a convolution of operators that were introduced by Braverman and Kazhdan, and they have the following form. So they depend on, let's see, they depend on parameters lambda that are non-zero integers, and s are complex numbers, and they're given by lambda factorial mu s f of x. I'm imagining my function as being some smooth function on xp, actually xp op in this. So this is the integral over m abelianized of f of psi omega p m omega p m s plus 1 delta p lambda over 2 f of m negative lambda g, sorry, x d m. Okay, so it's just this integration over the abelianization up to a normalization with the lambda. But because of this psi here, it behaves like something like a weighted Fourier transform. Okay. So this is exactly what we saw in the other setting. I'm not going to tell you how these, you need a particular convolution of these operators, and the convolution Convolution. I mean, maybe convolution is not the right word here. Maybe I should just say you just need a composition of these operators. And it's important, and this is a point that they don't need it, so they don't need to worry about it, but it actually, you have to compose the operators in the correct order, or else it's not well defined on the short space. And the data that goes into this into the definition is a certain representation of the Langland's dual of M on the Langland's dual of the Lie algebra of N. But fortunately, if you ever want to use this stuff, this paper that we wrote, we computed each of these parameters explicitly. So you don't have to actually know or understand this representation theory in order to know what the parameters are in any given circumstance. Okay. So I think this is actually a good place. I mean, I guess I'm a minute early, but I think this is a good place to stop for this time because there's a